Hello. Hello, hello. Cool. How's it going? This is the last video for Exam 2. Exam 2 is going to happen... I guess I should put this on Blackboard. It's going to be the same deal as last time. It's going to be Monday, 4 to 6 p.m. unless I hear that people can't do that. I guess I should say that in the group text. I'm going to talk about a couple homework problems people asked me to look at, and I'm going to go through the practice exam, and that's all I got for today. I might also go through the odd homework problems and probably not give full solutions to them, but just notes about this one converges, try the direct comparison test, this one, whatever. But here's a problem write-up submitted by Joe that we're going to take a look at. The series is n over 1 plus n to the 3 halves. The part you can't see here is that that's about n over n to the 3 halves is 1 over n to the 1 half. And the sum of 1 over n to the 1 half diverges. It's a p-series. The limit is 0, and he's computing the derivative and simplifying it enough to get to a point where you can say, hey, that's eventually negative. That's great. What's this text say? The series doesn't converge absolutely. Consider the sum of the absolute value of the terms is the sum of this without the negative 1 to the n. We show that that sum diverges by limit comparison using bn is 1 over n to the 1 half. We have this limit is, short version of working the limit is 1, check, since the sum of 1 over, I think that's a mistake. This says the sum of 1 over n squared. It should be sum of 1 over n to the 1 half. Maybe it says that and I didn't get a high-res enough screenshot. It's a divergent p-series. Sum of 1 over n squared is convergent. N to the 1 half is divergent. 1 half is less than 1, 2 is bigger than 1. We get that that series diverges, and the given series cannot converge absolutely. This is all great wording. Things to pay attention to. We're talking about this series, and this series, and this series. There are 3 series being talked about in this paragraph, and we're being clear when we're talking about which one. This one's a p-series, this one is comparable to a p-series, this one is the alternating version of that, right? But the given series does converge by the alternating series test. N over 1 plus n to the 3 halves is positive. We're talking about the terms now. Yes, they are positive. It has a limit of 0 since, yes, that limit is 0. Okay, I think what this says here is that the limit as n goes to infinity of n over 1 plus n to the 3 halves equals 1 over n to the 1 half equals 0. I feel like right here is a place where you're fudging things a little too much for my comfort. This thing is approximately 1 over n to the 1 half. The limit doesn't equal this sequence. Like, the limit equals 0. Like, this thing does equal this thing. This is not a thing that's equal to those two things. 1 over n to the 1 half doesn't equal 0. It goes to 0. I would much rather do the same type of thing you're doing here. That this limit is the limit of multiply the top and bottom by 1 over n to the 3 halves, n to the negative 1 half, n to the negative 3 halves, plus 1. That limit is 0 over 0 plus 1. Like there's a way of being precise there. That this particular little bit is not being precise. This limit doesn't equal that term. And is eventually decreasing since the derivative equals this. The numerator goes negative with the negative n to the 3 halves term, and the denominator is positive. Yes. The alternating series test does apply, and the series does not converge absolutely. Does that say but converges conditionally? But feels like a weird word to use here. It feels like you're stating another hypothesis instead of like drawing the conclusion from the first half, I would say therefore it converges conditionally, or so it converges conditionally, or maybe I'm just reading that word wrong. This looks really good. Good job. Exam 2 is happening Monday, 4 to 6, unless I hear wrongly from the schedule. Actually, I should just not say that it's going to be 4 to 6. Check your texts. I'm going to ask you if you're okay taking it 4 to 6. And if someone's not, I will ask if everyone's okay with another time. Let's go through the practice exam. I was not smart enough to pull that up first, was I? That is not the... Oh, I did! Hooray! Here's the practice exam. Here's a series. Do this stuff to it. Problem 1 is worth 63 points. There's lots of tests that work here. If you use the nth root test, if you use the ratio test, those will all work. The key thing to notice, though, is that this thing happens to be geometric. When the series happens to be geometric, I'm asking you to evaluate it. So being ready to notice that a thing is geometric, this is one of these places where the fact that it's geometric is a little hidden. This is 2 to the 1 times 2 to the n over 3 to the n. That's 2, a constant, times 2/3 to the n. A convergent geometric series. The sum is its first term over 1 minus r. When I plug in n equals 1, I get 2 times 2/3. That's going to be 4/3 is the first term. I'm plugging in n equals 1 because the series says it starts at n equals 1. The usual formula works for a series that starts at 0. I like using this first term thing. Works for any first term. 4/3 over 1 minus 2/3. That's 4/3 over 1/3. That's 4. And then what? And then we got this one. This one's alternating. It's usually really easy for an alternating series to converge. All you need is for the terms to go to 0. These terms are n minus 1 over n plus 1. That goes to 1. Is not 0. This series diverges by the divergence test. I need to justify why the limit of the term is not 0. I'd like to say the limit is 1, but once you stick the negative 1 to the n on there, the limit is not 1. It's like alternating between getting close to 1 and negative 1. So that doesn't work. Cool. If that's the right idea, it's just not an easy thing to phrase. The thing I would say is, so colon, here's the reason it diverges by the divergence test. Since the limit of n minus 1 over n plus 1 is 1, the limit of negative 1 to the n minus 1 over n plus 1, doesn't exist, and in particular isn't 0. Cool. You don't try and have to come up with words for the fact that it's alternating between approaching 1 and negative 1. The word for that is the limit doesn't exist, is all you need to say. What do I got here? N squared over root n plus n to the 4th. I want to be immediately thinking this is about n squared over n to the 4th is the big part of the top, is 1 over n squared, and the sum of 1 over n squared converges. This is about as big as something that converges. If I'm lucky, it's smaller than the thing that converges. Is it smaller? Versus n squared over n to the fourth. This is a bigger denominator, so it's a smaller fraction. Yes, it is. Hooray, we're in the lucky case where we're on the right side. We'll use direct comparison. We have that this term is positive, and it's less than n squared over n to the fourth is 1 over n squared. So our series, so the given series, converges by direct comparison. With the sum of 1 over n squared, comma, a convergent p-series. We know this thing converges because it is a p-series, and our thing converges by direct comparison with it. Cool. Ew. This is one of these cases where I think we're going to have to use the integral test. Yeah, hopefully you've done enough problems that you've seen this. We've got a 1 over x. The log x is making this materially smaller than 1 over x. Being smaller than infinity doesn't help us. But we're bigger than any higher power of x. So we're sandwiched between all the convergent p-series and all the divergent p-series. We need something stronger to figure out which side of the line we're on. And that thing is going to be the integral test. To use the integral test, I need 1 over x log x to the 9/7 to be eventually positive and decreasing, since x and log x are increasing. We have that x log x to the 9/7 is increasing. I'm multiplying, I can raise an increasing thing to the 9/7 and it's still increasing. I can multiply two increasing things and be increasing. That only works for things that are positive. Log x is not always positive, it's eventually positive. So I need some eventuallys in here, actually, to be correct. X and log x are increasing and eventually positive. So we have that this thing is eventually increasing and positive. So 1 over x log x to the 9/7 is eventually decreasing and positive. I'm about to start computing an integral. I should mention the integral test before I do that. We may use the integral test. I think it's sort of a bad idea to throw someone into a bunch of math without saying, what's the point of doing all this math? Oh, I guess I meant to say at the start, hey, if you haven't done the practice test, go do that before you watch this. The integral from, where should my integral start? I guess 5 is a decent place to start. The thing's eventually increasing in positive, as long as we're past the places where that goes to infinity, which are 0 and 1. 5 is past that, okay. 5 to infinity, 1 over x log x to the 9/7 dx is, I'm going to use the substitution u equals ln x, du is 1 over x. That turns into the integral from natural log 5 to infinity. of 1 over u to the 9/7. I'm going to write that as u to the negative 9/7 du. The integral of that is u to the negative 2/7 times negative 7/2. I want to evaluate that from ln5 to infinity. Here's the place where I should probably, like, if this was an exam 1 problem, or if this was a final problem, I don't want to write it like plug in infinity. I want to rewrite it as a limit as a thing goes to infinity. But we're in the middle of a much bigger thing. We're allowed to be a little more loose with how we write these things. This is 0 minus negative 7/2 ln5 to the negative 2/7. This is negative power of infinity. Like, so this is 1 over. I guess this is worth writing. This is the limit is b goes to plus infinity of negative 7/2 times 1 over b to the 2/7 minus negative 7/2 1 over ln5 to the 2/7 equals 7 over 2 ln5 to the 2/7 is not infinity. So the integral, and hence the series, converge. Converge or converges? I think this is a plural. This, and hence this, does this. Yeah, you treat this like a singular. Converges. Okay, I think that should be converges, not converge. Feels weird, I'm not sure about that. That 1 over 4 to the k. So, okay, this is alternating. There's a negative that's being raised to a k. That's a negative 1 to the k. So I need to be keeping in mind that there's way more possibilities since it's alternating. If it converges, does it converge conditionally or absolutely? I want to think about the series, the sum of k times 1/4 to the k. Does that converge? K is not that big. 4 to the k is huge. The bottom is way bigger than the top. Under most circumstances, I'd expect this to converge, and it does. And the series should probably converge too. It definitely goes to 0, so at the very least, this thing converges by the alternating series test. But probably the series converges also. How would I show that this converges? The ratio test? Yeah, the ratio test would work. The root test would work also. I guess let's do the root test. We'll show the series converges absolutely. The sum, k equals 1 to infinity of the absolute value of the things, which I'm saying because that's the definition of converging absolutely, equals the sum of k over 4 to the k. We'll show this series converges by the root test. I want to take the limit as k goes to infinity of the kth root of the absolute value of k over 4 to the k. Actually, you know what? The way the root test is stated, it sticks the absolute values on there. I guess I can really cut all this stuff. We show that the series converges absolutely by the root test. That works just as well. Here's a much shorter way of getting there. I forgot the root test has the built-in absolute values to handle the transition from the regular series to The regular one. Yeah. This is the limit as k goes to infinity of the kth root of k times 1/4, right? Take the kth root of that, or take the absolute value and it gets rid of the negative, take the kth root and it gets rid of the k. This is 1/4 kth root of k. The limit of the kth root of k is 1. That's one you should know off the top of your head for problems like this. The limit is 1/4 is less than 1. I think that's it, we're done. There's nothing else to say, right? Yeah. The limit you get is 1/4 is less than 1, done. Root test. That's a real short one. Four to the k over 3 to the k plus 2 to the k. I feel so bad for the poor Cal 2 students who always look at this and turn that into 5 to the k. That bottom is not 5 to the k. That bottom is about, which of those is bigger? 3 to the k. This is about the size of 4 to the k over 3 to the k. What does 4 to the k over 3 to the k do? Like that's 4/3 to the k, which would be a divergent geometric series. But in particular, 4/3 to the k goes to infinity. That gets bigger and bigger. So this thing probably diverges by the divergence test. How quickly can I show that the limit is not 0 for the divergence test? Like the thing is not itself geometric. I can't just say this is a divergent geometric series. Let's try this. The limit as k goes to infinity. I guess we do the normal thing. Multiply the top and bottom by the biggest thing on bottom. Or 1 over the biggest thing on bottom. Divide the top and bottom by 1 over 3 to the k. I get the limit as k goes to infinity. On top I have 4/3 to the k. On bottom I have 1 plus 2/3 to the k. The top goes to infinity. The bottom goes to 1 plus 0. The limit is plus infinity. The terms don't go to 0. So the series diverges by the divergence test. Yep, that's it. Here's G. I got a factorial that's pointing me at the ratio test. I'm just going to dive in with the ratio test. We use the ratio test. Actually, let's do the limit first. The n plus 1th term is n plus 1 to the 8 over n plus 1 factorial. I'm going to divide that by n to the 8 over n factorial. I get n plus 1 over n to the 8 times n factorial over n plus 1 factorial. That's n plus 1 over n. I guess, since I have the extra step, I might make it extra super obvious. That thing goes to 1 by splitting it into 1 plus 1 over n to the 8 times 1 over n plus 1, still with a limit out front. This limit is 1 times 0 is 0. That thing is 1 to the 8, the other thing is 0, or it's 1 over infinity is 0. So, the series converges by the ratio test. We find the limit of absolute value an plus 1 over an. I don't like writing that because I haven't defined an, and I don't want to go back as far as writing that. I guess we'll just say that we find the series converges by the ratio test. Done. Do I know what it converges to? I don't know what it converges to. My computer just made a sound that I don't know what it means. Everything going normal? We still streaming? Looks like we're still streaming. I don't know what that sound meant. I don't think it was lo-fi hip-hop. Beats to chill/relax to. Alright, we have an alternating series again. We had one alternating series that diverges. We've had one alternating series that converges absolutely. This is probably, like, if there's going to be 3 problems, I'm going to hit you with one of each, where one is the worst case scenario, where it converges conditionally and you need a ton of writing. What's going on here? What's the sum of 1 over log n do? It diverges. Is it obvious that this diverges? Well, log n is less than n. So this fraction is bigger than 1 over n, and the sum of 1 over n I know diverges because it's the harmonic series. That works, but the fact that natural log n is less than n feels maybe not so obvious that I can just say it without justifying it. And justifying it seems rough. Is there a more direct way to get that 1 over n diverges? Can I integrate 1 over log x? I don't really want to. I guess I want to show that log n over n, log n is less than n. If I needed to show that, then I'd be trying to show that log n over n is less than 1, and I can do that with L'Hopital's rule, because the limit of the left-hand side is 0. Ugh, this feels no fun because it's like a bunch of steps now to get that log n is less than n, to get that this diverges by direct comparison. But I don't really see a more direct way, unless I just want to say I know that log n is less than n, which is maybe a reasonable thing to say at this level of math. I'm going to justify it, though. We have that the limit as x goes to infinity of natural log x over x is, the limit is x goes to infinity of 1 over x over 1 equals 0 by L'Hopital's rule. I like specifying infinity over infinity version. Have I given my rant about how ridiculously lucky we are that L'Hopital's rule is only one rule? There's lots of ways you could define what a derivative is. Instead of talking about slopes, we could have been talking about angles. We could have, there's like the idea of slope being rise over run is sort of one arbitrary way of thinking about angles of things. And the way we picked it is one where L'Hopital's rule is take the derivative of the top over the derivative of the bottom. Miraculously works both for infinity over infinity and 0 over 0. It's just crazy that it's the same rule, and it's just derivative of the top over derivative of the bottom. It is such a simple rule. Oh, I was going to tell you, I said I was going to save it for later, the story about L'Hopital's rule. L'Hopital wrote what was probably the first math textbook. Bernoulli had discovered the thing we call L'Hopital's rule. L'Hopital bought the naming rights to it. He bought his name onto L'Hopital's rule. He paid Bernoulli to say, hey, can I say this is my rule? Yeah, okay. I think that's funny. The funniest part is we still call it L'Hopital's rule, even though we know it's not his. We have this by L'Hopital's rule, so for large x, we have ln x less than x, or log x over x less than 1. So ln n is going to be less than n for large n. Thus, the sum, or 1 over log n, is going to be bigger than 1 over n eventually. And so the sum of 1 over log n diverges by direct comparison with the harmonic series So the given series, the sum of negative 1 to the n, 1 over log n, does not converge absolutely. I like putting a paragraph break here. Like, we just showed that this thing does not converge absolutely. Now we're separately going to show that it does converge. 1 over log n is positive, eventually decreasing, since log n is increasing. Why am I using the word eventually here? This feels maybe... Where did my other... Did I swallow up my color palette? I can usually switch colors, right? Toolbars. Format. Where'd it go? Oh, come back. There we go. I wanted a purple line. Yeah. Why am I saying eventually? I think it's probably not necessary, but what's going on here is that I know that when something is increasing, its reciprocal will be decreasing if the thing is positive. Natural log is not actually always positive. It only starts being positive after 1. So I'm being a little bit fuzzy in covering my bets. I don't really need to do that because this series is only starting at 2. It couldn't start at 1 anyway because then we'd be dividing by 0. But this is the reason I'm fudging in and eventually. Natural log is increasing and eventually positive. That only gives us that 1 over log n is eventually decreasing. If I look at 1 over this function, it'll be... I'll do that. It's going to have a pole at 1. So this thing is a decreasing part. But it's also got this thing going on here. Does that go like that, I think? I'm not sure what it does at 0 off the top of my head. But, I mean, this is a thing that's decreasing after you get past the place where it was negative. The place before it was negative is decreasing too, but the hop from here to here is an increase. There's a possibility the thing isn't always increasing because natural, yeah, I've said enough. Since natural log n is increasing. That's why I'm using the word eventually here. And the limit of 1 over natural log n is 0. So the sum of negative 1 to the n, 1 over log n, converges by the alternating series test. Thus, the sum negative 1 to the n, 1 over log n, converges conditionally. Most of the examples I'll restate in my final paragraph. It converges, but it doesn't converge absolutely. That means it converges conditionally. Well, the very last thing I said was it converges, and it was only 2 lines above that I said it does not converge absolutely. So because those are still such in recent memory, I feel like I can get away without reminding the reader, why do I know the thing converges conditionally? If you just read your way to here, then you just saw those facts, so you probably remember them. Let's find the radius and interval of convergence of this power series. I'm going to use the ratio test or the root test. Either one. Either one? Yeah, either one works here. There's no factorial, so it really could go either way. Let's use the root test. I want the limit as k goes to infinity of the kth root of the absolute value of 7 to the k over k squared times x minus 2 to the k. All the absolute value distributes on all this stuff. I get kth root of 7 to the k is 7. Kth root of x minus 2 to the k will be x minus 2, but it's in absolute values because there's absolute values around the whole thing. Kth root of k squared is kth root of k. And I can pull the squared out. Power to a power, the order doesn't matter. I want to pull the squared out because this thing is the thing I'm allowed to say right away that I know is 1. This is the limit of this, which is 7 over 1 times absolute value x minus 2. Is 7 absolute value x minus 2. This converges absolutely when that 7 absolute value x minus 2 is less than 1. So let's solve that. That's absolute value x minus 2 less than 1/7. That's x minus 2 between 1/7 and negative 1/7. Let's add 2 to all three sides. 2 and a 7th is 15/7. 2 minus a 7th is 13/7. There's most of our interval of convergence. Our radius of convergence is, I want to imagine this is a peg tied down at 2, which reaches out by a 7th on either side. So the radius of convergence is 1/7. To find the actual interval of convergence, I know it's going to be from 13/7 to 15/7, but I don't know if it actually converges at those. I need to test those individual points. So what's happening at x equals 13/7? This sum turns into the sum of 7 to the k over k squared, 13/7 minus 2 to the k. This is 7 to the k over k squared. 13/7 minus 2 is negative 1/7. That's where that number came from. 7 to the k over 7 to the k cancels. I'm just left with a sum of negative 1 to the k over k squared. That converges absolutely. If I stick absolute values on it, I get the sum of 1 over k squared is a convergent p-series. What's happening at x equals 15/7? I get the sum of 7 to the k over k squared, 15/7 minus 2. I subtract those, I get the sum of 7 to the k, k squared, 1/7 to the k. This is just the sum of 1 over k squared. It's not even an alternating p-series, a convergent p-series. So it converges at each of the endpoints. The interval of convergence I can spell the word convergence, is 13/7 to 15/7 with a bracket on both ends. Cool. Cool. What do we have for B? We have this thing. I got a factorial. I'd way rather use the ratio test than the root test. I accidentally hit the volume while I was muting myself to burp. Now I have to wait for that to go away. I muted myself when I burped. I'm getting real good at that. Please don't bring up all the times I didn't do it. Ratio test. Just let me feel good about the times I did. I want to talk about the limit as k goes to infinity of absolute value of k plus 1th term, x plus 1 to the k plus 1, over k plus 1 factorial, divided by absolute value of the kth term, x plus 1 to the k over k factorial. This is the limit, as k goes to infinity, of absolute value of x plus 1 to the k plus 1 over x plus 1 to the k times k factorial over k plus 1 factorial is the limit, as k goes to infinity, of absolute value of x plus 1 times 1 over k plus 1. This limit is absolute value x plus 1 as a constant. This limit is 0. This is 0. Sometimes we have to think about special cases, about what if you're multiplying by 0, then it doesn't go to infinity. That's not happening here. Maybe x plus 1 is 0. That just makes this go to 0 even better. The ratio test gave me a limit of 0 no matter what x is. It converges when that thing is less than 1, which is always. The interval of convergence is negative infinity to infinity. The radius of convergence is infinity. This thing always converges. Cool. Do we have a third one? We don't. If there was a third one, it would be a good guess that that one converges never, and the radius of convergence is 0. There's 3 possibilities. Radius of 0, radius of infinity, or radius of a number. The number one is the hardest. Let's evaluate this power series. We don't need to find the radius or interval of convergence, but very often we just get that as a byproduct. I will note it if we do, because maybe your exam will want the radius or interval. What can I do? Oh, this thing's just geometric. If I pull off that extra x, this is x times 5x to the n, right? It converges on when 5x is between negative 1 and 1. That's when x goes from negative 1/5 to positive 1/5. That'll be the radius of convergence. And the series adds up to first term over 1 minus r, which is here. The first term is when n equals 3 is 125x to the 4th over 1 minus, our common factor is 5x. That's what the series adds up to. That's when it adds up to that. Cool. That was an easy one because it's already geometric. This one is not already geometric. To find a power series expansion for this, the hint says take a derivative of it. Derivative of tangent inverse is 1 over 1 plus blah squared times the derivative of the inside. That's 2 over 1 plus 4x squared. I want to make this look like my geometric thing, which is 1 over 1 minus blah. So this is 1 over 1 minus negative 4x squared. This is going to be the sum of 2 times the sum of that thing to the n. If I go from 0 to infinity. My thing is negative 4x squared. This is the sum from n equals 0 to infinity of 2 times negative 4 to the n times x to the 2n. And that's g prime of x. So g of x is going to be the integral of that up to a constant. It's a constant plus the sum from n equals 0 to infinity. Keep in mind that I'm integrating with respect to x, so this stuff is a constant. It's not constant with respect to the n, so I can't pull it out of that series, but that's not how I'm integrating. I'm integrating with respect to x, and it is constant with respect to that. 2 times negative 4 to the n, I need to divide by the new number, 2n plus 1, x to 1 more than that, x to the 2n plus 1. And how do I find that constant? I plug in 0. G of 0 is going to be c, needs to be Tangent inverse 0. Tangent inverse 0 is 0, so C is 0. So g of x is the sum from n equals 0 to infinity, 2 times negative 4 to the n over 2n plus 1, x to the 2n plus 1. This only uses odd terms because it is an odd function. Tangent inverse, if I graph it, looks like this. It's got rotational symmetry, it's odd. Its power series only has odd terms. I guess we never stated that, but sine is an odd function, and its power series only has odd terms. That's a thing. Find the third Taylor polynomial of this, centered at this point. This is weird, that thing's already a polynomial. Usually I want to find Taylor series of things that aren't polynomials. That's the interesting case. For the third Taylor series at x equals -1, the thing is going to be g of -1 plus g prime of -1 x minus -1, g double prime of -1 x minus -1 squared, this is over 2 factorial, g triple prime of -1 over 3 factorial x minus -1 cubed. That's the third one. I know all the pieces of the setup except for what are these numbers. I work these numbers by taking that function and working out its derivatives. G of x is x to the 5th, g prime of x, 5x to the 4th, g double prime of x is 20x cubed, g triple prime of x is 60x squared. That's as far as I need. G of -1 is -1. Prime of -1 is 5, g double prime of -1 is -20, g triple prime of -1 is 60. So, sticking all those in, I get T3 of x is, g of -1 was -1 plus 5 x plus 1 plus -20 over 2 x plus 1 squared plus 60 over 6 x plus 1 cubed. You could reduce those. We don't want to reduce them. There's the third Taylor polynomial. Cool. And that's the end. There was also... Someone asked me to do a homework problem, and I should have done that before this, but I forgot to. Number 121 on power series. Oh, this is a hard one. This is a really good problem, by the way. We're going to use the ratio test. This factorial is an indication that we should use the ratio test. One of the things you might think about, like this x to the k is the thing that's always there. I got a k factorial over over k to the k. In my list in my head of how fast things go to infinity, those things both go to infinity really fast, but k to the k is bigger. K to the k is k times k times k times k. K times. Versus 1 times 2 times 3 times all the way up to k. K factors. This should be way bigger than the bottom one, right? Like, it's k over 2 times bigger. Times k over 3 times bigger. Like, those get bigger and bigger. So this should be much, much, much bigger than the bottom. It's actually not as much bigger as you would expect. Let's see what happens when we use the ratio test. Ratio test. thinking about the limit as k goes to infinity of the k plus 1th term, k plus 1 factorial, x to the k plus 1, over k plus 1 to the k plus 1, that's obnoxious, divided by the kth term, k factorial x to the k over k to the k. Can I understand this? Okay, what is this? This is the limit as k goes to infinity of k plus 1 factorial over k factorial. Those are positive, I don't need the absolute values on them. I'm going to have k to the k over k plus 1 to the k plus 1 times x to the k plus 1 over x to the k. These ones are in absolute values. Okay, first off, this thing cancels to make a k plus 1. One of these k plus 1s cancels with one of those k plus 1s on bottom. X to the k plus 1 over x to the k. This is just absolute value x. So we got the limit as k goes to infinity of absolute value x, which I can just pull out of the limit. This is a constant. I can pull it out as long as it's not 0. If it is 0, then even if this limit turns out to be infinity, the 0 wins. But I'm just pulling it out of the way now. Like I can't justify pulling it in until I think about if x equals 0. Or know that the limit is finite. What do I get? I get k over k plus 1 to the k. What is this limit? The inside is a rational function, the leading coefficient, the degree of the top equals the degree of the bottom. The thing inside there has a limit of 1. This is like a 1 to the infinity case. 1 to the infinity was one of these obnoxious, difficult indeterminates. The reason it's difficult is if you have a number slightly bigger than 1 and raise it to the infinity, you get infinity. If you have a number slightly smaller than 1 and raise it to the infinity, you get 0. If you get a number that equals 1 and you raise it to the infinity, you get 1. Whether it goes to 0 or infinity or 1 or something in between kind of depends on the rate at which something goes to the 0. How fast does this go to the 1 and how fast does that go to the infinity? So we're going to need a tricky thing, and this is the place where you stick in an e to the and a log to use L'Hopital's rule. This is e to the natural log of that thing. This is absolute value of x times e to the, I'm using exp for e to the, so that I don't have to write all this mess inside an exponent. This is a useful thing to know. Exp of, the k falls off the log. I can write ln k over k plus 1 over 1 over k maybe? I mean, it's k times it. When I have k times this, I'm going to be infinity times 0 case. So you fix infinity over 0 by pushing something to a denominator. I'd rather have to take the derivative of 1 over k than have to take the derivative of 1 over natural log. The natural log's already easy to take the derivative of. At some point I need to change those k's to x's to use L'Hopital's rule. Let's consider the limit. Since I'm switching names, this is also an opportunity to just zoom in on the part we want to talk about. Let's talk about the limit as x goes to infinity. Natural log x over x plus 1 over 1 over x. This is, the bottom goes to 0. The top goes to natural log of 1 is 0. This is an 0 over 0 case for L'Hopital's rule. Before I take the derivative of the top, I want to split the logs up. We're doing something a little bit fishy here. This is the version that I can look at and say, hey, the top goes to 0. When I split up the top, it's not nearly as obvious that the top goes to 0, but the top is the same thing as it was. If I just said the earlier version goes to 0, this version must go to 0 as well. This version is just more convenient for taking the derivative of. Taking the derivative of this will be the same as taking the derivative of the other version, because they are equal, but it feels fishy to do that, because now it doesn't look like as obviously that it's 0 over 0. But it is because the top one was 0 over 0. This isn't a thing you need to write out a justification for. This is just me warning you. This is, now use L'Hopital's rule. Limit as x goes to infinity. The bottom, the derivative of that is negative 1 over x squared. The top, derivative of log x is 1 over x minus 1 over x plus 1. This is the limit as x goes to infinity of, multiply the top and bottom by x squared, I get x, negative x squared, I get negative x plus x squared over x plus 1. I guess I want a common denominator. Minus x plus 1 plus x squared over x plus 1. This is negative x squared minus x plus x squared over x plus 1. The x squareds cancel. Limit of negative x over x plus 1. Degree of the top equals degree of the bottom. The limit is leading coefficient over leading coefficient is negative 1 over 1. Boo! So the earlier limit is, limit is k goes to infinity, absolute value of x, e to the, something that we just concluded goes to, negative 1. It's absolute value of x over e. Converges when absolute value of x over e is less than 1. That's from x goes between negative e and e, is our interval of convergence. Or our radius is e. The interval is negative e to e, give or take some parentheses and brackets. If I think about what's happening at negative e and I think about what's happening at e, oh geez, is this hard? Huh. These endpoints are hard. I did not notice I put something this hard on here. All right, what's happening at negative e? I get the sum from k equals 0 to infinity. Of k factorial, e to the k, k to the k, minus 1 to the k. If I use the ratio test on this, I'm going to get 1. Like, that's the key thing, is, like, this is the exact same thing. I just used the ratio test, and at the end point, I got 1. And I don't feel like I have good tools to use other than the ratio test. Is this problem a mistake? Did I have less instructions? The radius and interval of convergence. Yeah, I said to find the interval, and I can't do it for 121. Did I have a version of the problem where... Yeah, this is the dumb thing I did. Oh, no, okay. 93, I put n factorial over n to the n. So I meant to put this problem here. I think maybe last year I said, maybe this is hard, I should save it for later. But the harder version of the problem is way too hard. Let me show you the thing I really wanted you to notice from this problem. There's a specific crazy lesson to learn. When you take when you do the ratio test on this, the ratio test is telling you that maybe this thing is about a constant times something to the n. And you're trying to find what is that r. You say, what is the new term divided by the previous term? Something is exponential when you're multiplying by the same thing over and over. Is this multiplying by the same thing over and over? What is it you're multiplying by to get from one term to the next term? This is why you take that ratio, new term divided by last term. And that ratio turns out to be e. We're finding that n factorial over n to the n is about a constant times e to the n. This thing is really close to being an e to the n type thing. So here, but asking what is it doing at the, did I have? Or it's 1 over e. It's about a constant times 1 over e to the n. But when you move that e to the n to the other side, this is a thing that you expect to be about constant. This is a hard limit. I should take this off the homework. It's reasonable to get the radius of convergences from negative e to e. It is a hard problem to figure out whether it actually converges at e or at negative e. If it converges at negative e, then it definitely... If it converges at positive e, then it definitely converges at negative e, because it'll converge absolutely. I don't know if this thing does. I think this is... If you're interested, Google a thing called Stirling's formula. It's a pretty good approximation of k factorial, using this fact that k factorial is about k to the k over e to the k. There's like an extra square root k or something in there. So I think the thing will end up being, if you knew Stirling's formula to work it out, you can compare it with a p-series, which I think will diverge. But yeah, that's way beyond this class. Sorry, that problem's too hard. You can at least get the radius as e, but it is a very difficult integral. I'm going to stop lecturing here. I have ambitions to, at some point, tonight or tomorrow, make up some notes on the odd homework problems. Probably not giving complete solutions, just sort of, here's what the answer is going to look like. I may stream myself doing that. I might not stream myself do it. I'll figure out what my mood is. I don't think there's much. It's not like with an integral where you want to watch the process. I'm just going to write down the answers. So look for that on Blackboard soon. I'm going to text you about exam times, but I'm thinking, we did it at 4 last time, right? I think everyone was okay with 4 last time. Hopefully everyone's okay with 4 this time. I'll text you. I'll stop talking now. See ya.